Good afternoon. I hope you're enjoying PyCon. Welcome to Opening the Black Box in Interpretable Neural Network Architecture. I'm going to introduce myself briefly, and then we're going to talk a bit about neural network limitations. Then I'm going to introduce a new type of neural network architecture, which has built-in interpretability. So it's a simple neural network, but its architecture is slightly different, as you will see, and allows more interpretability. We're going to see some real-world applications and some more directions that we can take this idea. So quickly about myself, I actually come from a social sciences background. I studied psychology and social sciences and humanities and transitioned into data science about five years ago. I actually believe that my social science background is very beneficial for my work as a data scientist, exactly for the kind of reason that we will see today. As a social scientist, I'm used to trying to understand the data and to interpret it more. People from a computer science background have the tendency of just trying to optimize a metric, not trying to generalize too much here, and some of you are okay, but a lot of people try to optimize the metric without really understanding the data. And sometimes understanding the data is very important. And in the end, for production reasons, for improving your metric, in understanding the data and why it behaves the way it does and where your model fails is more important than just trying to optimize a metric. So in the past few years, I've been working as a senior data scientist at Anaplan. Anaplan is an international corporation in rapid growth in the past few years. We're hiring. It's a really great place to work at. So if you're talented, please join us. So neural networks. I assume everyone is familiar with neural networks here. It's the data track. Neural networks are great and are used for a variety of problems. The power is that they can solve nonlinear problems as opposed to a linear regression. And that's kind of the clever thing about neural networks, is that they're made of these components that are basically just linear regressions. But because of the structures and the layers and the nonlinearity that we apply on like a softmax or logistic function or whatever that we apply on the layers, we can achieve any kind of nonlinear solution. We can emulate all kinds of nonlinear functions. The problem is that the generic neural network, just these basic layers, has very little interpretability, as opposed to the linear regression that is actually the basic component of neural network. However, the beauty, I think, in neural networks is that they are very, very flexible. They are basically just like Lego blocks that you can compose in all kinds of different ways. And that allows us to redesign the architecture of a neural network to be significantly more transparent. So the neural network will actually explain the decisions that it makes, so we can really understand what's going on behind the scenes. So how do we accomplish that? Well, first, let's look at this example. We have X and Y. There's some relationship between X and Y that is clearly nonlinear. Now, we're going to start with an example where X has one dimension, which is easier to graph and understand what's going on. And we will then generalize to a case where we have multiple features. So for now, there's only one feature, X, as you can see here. And Y is some polynomial of a high degree over X. And if we try to solve this problem using a linear regression, it's going to perform quite poorly, naturally. So linear regression doesn't work well. What do? A lot of people will turn to trees. So random forest, like GBMs, all kinds of trees, XGBoost or all trees. They're a really common go-to, but they don't always fit the data. And that's something that you should remember. Sometimes data behaves in a way that is tree-like, but sometimes it doesn't. Sometimes it behaves in a way that's more linear or exponential or other ways. And if you try to force it to be a tree structure, a tree model, it's not going to generalize very well. That's what you can see here. So firstly, I took the X's in this range and I randomly sampled 80% and trained random forest on them, and then tested on the other 20%. And as you can see, it has quite significant overfit, doesn't generalize well. But let's say that's even relatively understandable. Imagine that this is the range that we got during training, but then in production, in prediction, sometime down the road, we're going to get a value that exceeds this range. Okay, maybe the range here is somewhere between -6 and 6. What if you get like 10 now? Because of the tree-like nature of the model, it's going to give a horrible prediction. As you can see, it's just going to give probably the exact same prediction for all of the values above a certain threshold. That's how the trees work. So it's going to generalize very, very badly because we didn't think about whether a model fits the problem. So what can we do? Well, neural networks are nice, and that's what a neural network will do. It fits the data quite well for tests as well, except that it has little interpretability. Now, in this case, we don't really need interpretability, and we can graph the data and understand it quite well. But as we will see later, neural networks don't, we can find better ways of interpreting this and more, and examples with more dimensions. So how can we do that? Well, we're going to start with a simpler idea of the model, and it's going to get slightly better. The basic idea that I have in mind when I see this sort of graph is that I would like my model to break it down into maybe 3 parts with a different slope for each part. So I can see that in the beginning, there's a clear negative slope. And then there's a slope that's close to 0, and then there's a clear positive slope. Now, we can easily do that. We can just split it into 3 parts and create a linear regression for each area. But I would like the model to do it by itself, to find the breaking points by itself, and also to be generalizable, so it can be more than 3 or 4 or 5 different areas where every area is linear in itself. And also to generalize it to a case where we have more than a single dimension for X, in which case we can't even plot it easily. But it's important to note that if we could achieve something like that, if we can achieve something that has a slope for every area, it'll be much more interpretable. Because if I tell you, okay, for this X, the slope, the coefficient of the regression for this area is 9 and 5 is something like that, you can understand what's going on in that area of X much better than the neural network that doesn't give you anything except a prediction. So how do we do that? Well, we imagine the relationship between the input and the output is linear, except that the coefficients can change. They depend on the exact X where we are. So what we really have is multiple different potential regressions, and then one of these regressions is selected per a given X. Okay, now it doesn't actually have to be selected in a binary way, so just one regression. We can have a sort of weighted mean of the different regressions where we place a larger weight on the correct regression for every given point. So this is a small graph of this idea. We have the input feature, in this case, again, only 1. And then we have 3 possible slopes, so coefficient for the regressions, giving us 3 potential results for the regression. And then we also have a selector vector, which sort of gives a percentage of how likely each regression is, how good that is. And then we can take a weighted average of these regressions based on this selector, and that's going to be our final output. Okay, so the number of regressions that we can have is configurable. In this case, we have just 3, but we can have as many as we want. Now, once we have that idea in mind, we can easily generalize it. The same structure applies to a case where we have multiple inputs, and we will see an example with that later. So how do we accomplish this? Well, again, that's the beauty in neural networks. The beauty is that they're just these simple Lego pieces of basically linear regressions, and we can put them in any way that we would like. Basically, a dense layer, a simple linear layer in the basic building block of regression is just multiple linear regressions from your input, from the previous layer, to as many neurons as you would like. So a simple dense layer is exactly that, as many potential regressions as we would like. We can also create a dense layer from the input to this selector, but then apply a softmax operation on the selector. And the softmax makes sure that all of the items all the elements in the vector sum up to 1. And usually there's going to be one significant element that's going to be much stronger. So that gives us what we wanted, this sort of percentage of how likely, how well each regression fits this specific X. And now we just take the dot product of these two vectors, and that's our output. And the beauty of neural networks and libraries such as PyTorch and TensorFlow is that once we describe this architecture, we can use basic gradient descent or Adam, all kinds of optimizers for finding the right parameters for these regressions, for the potential regressions, and for the selector regressions. So just two dense layers, but instead of having them sequential, they're sort of parallel, and then softmax and multiply. So what does that give us? Well, this is the result. It's actually smoother than what I showed as the general idea guiding this approach, because the selector, as I said, isn't actually binary. It doesn't have to be a single slope, a single coefficient for every X. It's a combination of the different regressions. So every X gets its own unique regression. It's still a linear regression for every X, but it's unique for that specific X, slowly changing from the very negative slope to a more positive slope and so on. So that's what we got from, if I trained this model, okay, we get these different coefficients for the potential regressions and the coefficients for the selector. And this tells us quite a lot, I think. So let's just put them in a data frame like this and try to see what the data frame, what the network is telling us. Well, let's start with the selector coefficients. So these are the coefficients that determine which element in our selector vector is going to have the strongest weight, and then it's going to select the right regression. Okay, so we have this regression number 1 here. The coefficient for it is negative. So when is the element number 1 going to be the highest? When is it going to be the strongest in the vector? When X is clearly negative. The more negative it is, the stronger this element will be. Element 2 will be strongest when the X is positive. And the higher positive it is, the stronger it will be. You can see these examples here. So these are different X values. And this is what the selector gave for each one of these elements. And then according to it, it aggregates it finds the mean, the weighted mean of the regressions. So when it's a strong negative, the first regression will be the strongest. When it's a positive, it's the second one, and the 0, 1 somewhere in between. Now, even before we go on, just think about a world where I didn't show you the graph that we're trying to fit. Okay, if I just tell you this, you now understand that in general, our graph very roughly looks like 3 different areas, where one area has a slope when it's negative and one around 0 when something else, and then another area where it's a strong positive. These are 3 areas of different regressions where there's a different relationship between X and our target. Now we can see that, now we can look at the regression coefficients, and we can see that indeed when X is negative, this regression will be selected, and the slope will be a strong, clear negative, the slope selected. When X is positive, this regression will be selected, and the slope will be a clear positive. So that makes sense. It makes sense for the graph that we've seen, and we got quite a bit of interpretability for compared to a normal neural network, and we got basically the same results as a neural network, as a vanilla neural network. So let's move on to to a more real-world example, the Boston housing data set. Many of you may be familiar with it. It's a very famous data set, about 500 examples in it. The target is to predict the price of a house. And you have all kinds of features like distance to city center, crime rate, number of rooms, retail businesses around the house, and so on. Now, when I see a data set like this, I don't imagine that features behave very tree-like. I think it's unlikely that distance to city center or crime rate or things like that behave very tree-like. So I prefer to avoid a tree-like model. I prefer something that's a bit more smooth, a bit more linear, perhaps. Then again, a simple linear regression obviously will not perform very well because maybe different neighborhoods have their different preferences. Maybe there are interactions between the different features. So it makes sense maybe to cluster the data into like different neighborhoods. And then every neighborhood maybe has its own regression or something like that. And that sort of reminds us of what we just did. We have a different cluster. Every area has its own regression. So when I tried running this data set with a linear regression, random forest, and this multi-regression network, these are the results I got. As you can see, random forest overfits quite a bit, and the multi-regression network works quite well. So that's again when k was 3, we had 3 regressions combined for every x. Now, to be fair, I didn't try like GBM and didn't try to optimize the hyperparams too much. I just used the default of all of these 3 models. But the point is not so much what's the best model to get the best metric for this specific data set, but my point is more about the interpretability that we're going to see. So I trained the network, and whereas before we only had 1 coefficient per regression or selector, now we have a few because we have multiple features. So we have these 13 features, and for each of these 13 features, there are 3 different regressions, potential regressions, and then there are 3 selector regressions that will decide which element in the vector will be the most influential. So which regression will be selected. Again, I just used k equals 3. You can use a greater k, which will allow more complexity. It doesn't really harm interpretability, I think, but we don't have a lot of time to analyze this data so much, so I prefer to use a simple example. Now, 13 features are way too many, so let's only focus on 4. And what I did here is I took 4 examples from each of the different clusters. So again, the selector, just looking at the results of the selector, the selector will output how likely each regression is. And we can just focus on the selector and see how it clustered the different examples. So which samples went together, which samples will have a similar regression later on. So these are just 4 examples from each of the different sort of clusters according to the selector. The values here are normalized. That's why you can have a negative number of rooms. That means that you have fewer than the average number of rooms, simply. And when we look at this, we can sort of make sense of it. We can see what the selector was trying to do. So the cluster 0 is all stuff that are relatively close to city center. So it's a negative distance, meaning lower distance than the average. So they're relatively close to city center and medium number of rooms. Cluster number 1 all has few rooms. Cluster number 2 have lots of rooms and low highway access. So for every cluster, we can understand what it looks like. And it makes sense to us now. So there's a different cluster. Every cluster will have its own regression. Again, they're kind of mixed together. So it's not a single regression, as we've seen, not a single slope for every item. There are a mix of the different regressions. But in general, there'll be one that's most dominant for every cluster. So now we can look at the selector coefficients and the regression coefficients. And we don't have a ton of time to go over all of the features, but I'll just show you the basic idea of how you can interpret something like this. So we can look, for example, at the selector cluster 1 and 2, right? What will select either the first the regression 1 or 2 in this case. And we can see that the selector tends to have the same coefficient for both of these clusters, except for the number of rooms. That's where they're different. So one of them has fewer than average rooms and one has more than average rooms. And what does that translate into? So what are the regressions that you'll have if you have few rooms compared to if you have multiple rooms, if you have more than average rooms? Well, if you have few rooms, it looks like highway access is very important to you. That's going to be a positive coefficient in your regression. If you have lots of rooms, then highway access is not so important. It's actually even harmful to some degree. And what is important to you is non-retail businesses. That's what you really want to have. So maybe like factories and other places where you can work. What the selector seems to have done is maybe separated Boston and the Boston area into different towns and neighborhoods, areas would have different priorities. So maybe a suburb and the city center, for example. And within such group, you have different priorities. One, maybe in the suburbs, highway access is not so important. You want to stay in the suburb, but you want to have places where you can work. Whereas in the city center, that's not as important. I don't know. I don't really know Boston that well, so I can't really interpret this fully. If someone did know Boston, they can use this to really understand where this is all going, and you can look at the different features in more detail. But I just want to show the general idea of how you can use this method to interpret the nonlinearity of the network. So this is the PyTorch code. It's not a PyTorch tutorial, so I'm not going to go over it in too much detail. I just want to show how simple this really is. So when you define this multiple regression class, this model, you have to just define a linear or dense layer, and you tell it the input dimension, 1 in the first example and 30 in the second, and the number of regression that's completely configurable, as we said, as many regressions as you want. And you create another selector regressions, which is again just a linear model, a linear layer, and a softmax. And when you a forward pass over this network is just applying the regressions to X, getting the potential regressions, applying the selector regressions onto X, and then a softmax on that. That's the selector. You multiply the two together, and that's it. That's the result. And PyTorch has a simple way of then optimizing this and finding the best parameters once you define the architecture. So what did we find? If we had data, as I said, on like neighborhoods or different areas in Boston, maybe it would have made sense to cluster them together and then have a linear regression per area, and that would be incredibly interpretable. We don't have that, but the multi-regression network seems to have found this area as a sort of latent variable. It's found these different preferences, different clusters that behave in a similar way. So now we get, for every item, we can look at the regressions that it got and the selector value. And what we really get is every item has its own regression and an explanation why this regression was selected, what features caused this regression to be selected. The network basically clustered all of these items together based on the relationship of the features to the target. And that's really important, because if we try to cluster them using like k-means or some other clustering, then all of the features would have the same importance. But maybe we want to ignore features that are just random or not related to the target. Maybe what's important to us is clustering based on relationship from features to target, in which case this method can be used maybe even just for clustering. Maybe you don't care about the actual prediction, you just want to cluster based on relationship from features to target. So that's another way of clustering in general. So what we really have done here is we've decomposed the nonlinearity of the neural networks into two different linear parts, and thus preserved the nonlinear power of a neural network, but also preserve the interpretability of it. Now you can use this idea in all kinds of ways. You can replace the selector or the regressions with a neural network. So the selector will select the right neural network, or you will have simpler regressions and this selector will be a neural network. If one of the interpretability of one of them is not important to you and you just want to get a better result, you can make the selector truly tree-like. This kind of reminds the idea of linear model trees, if you're familiar with them. or you can replace the regressions to make them completely tree-like. You can take this in all kinds of directions. You can add regularization, which always makes sense. These are all good ideas. If you want to see the code for the multi-regression network, that's my GitHub account, so you can find it there. And just as a general message, I recommend that don't be too generic when you apply neural networks. You can think about these Lego blocks and compose them in different ways. There are so many ways to be creative with your neural networks for any specific purpose. If you're trying to cluster while you predict or do anything else. So thank you, and I hope you're enjoying PyCon. Thank you.